Understanding standard deviation made intuitive. Welcome, I'm Gianluca Malato, and in this lesson we are going to demystify one of the most important ideas in statistics, standard deviation. You've probably heard that it's a measure of spread, but what does that really mean and why should you care? Behind the scenes of data science, finance, machine learning, and scientific research, standard deviation quietly drives many of the tools we use every day, from measuring the volatility of a stock to understanding how consistent exam scores are, to quantifying the noise in sensor data or model errors. In this video, we won't just look at formulas. Instead, we'll build an intuitive picture of what standard deviation actually measures, how far data typically sit from their average, and how that typical distance affects the way we interpret and compare datasets. By the end, you will be able to look at a collection of numbers and immediately have a much clearer sense of how variable, stable, or risky they are, using standard deviation as your main lens. Welcome! On this slide, I want to give you a clear idea of what we are about to learn and why it matters. Standard deviation is a single number that tells you how much your data typically vary from their mean. In other words, if you know the average, standard deviation tells you whether most values stay close to that average or whether they tend to wander far away. Think about a few everyday situations. For stock prices, standard deviation is closely related to volatility. Do prices move gently or do they jump up and down a lot? For exam scores, it tells you how consistent students are. Do most scores set near the class average, or are there many very low and very high marks? For sensor measurements, it summarizes how much readings fluctuate around a stable value, helping you understand noise. By the end of this lesson, you'll have an intuitive picture of what standard deviation measures and why it's such a crucial building block in statistics and data analysis. On this slide, you see two very small datasets, each shown as dots along a number line. On the left, all 5 dots are stacked at exactly the same position. This represents the dataset 555555555. Every value is identical, so once you know the mean, you actually know every single data point. There is essentially no variability. On the right, you see 5 dots spread out across the line. This could represent 1, 3, 5, 7, 9. Notice that the central dot lines up with the cluster on the left. Both datasets share the same mean. But here, values are scattered away from that center, some smaller, some larger. These two examples make a key point. Knowing only the average is not enough to describe a dataset. Two datasets can have the same mean and still behave very differently. We need another number that tells us how spread out the values are around that mean. Standard deviation will be exactly that, a numerical summary of how concentrated or dispersed the data are around their average. Now that we've seen why the mean alone isn't enough, let's clarify exactly what standard deviation measures. On this slide, each dot is one data point placed on a number line. The vertical marker shows the mean, the average of all these points. Notice the arrows from each dot to the mean. Each arrow represents a distance, how far that particular value is from the average. Standard deviation takes all these distances, combines them in a specific way, and gives us a single number that describes a typical distance from the mean. If most of the arrows are short, the points stay close to the mean. In that case, the standard deviation is small, and the dataset has a low variability. If many arrows are long, the points are often far from the mean. Then the standard deviation is large, and the dataset has high variability. So conceptually, you can think of standard deviation as how far on average do my data points tend to sit from the mean. Some data assessing. On this slide, I want to connect the idea of typical distance from the mean with the actual calculation behind it. Look at the little table. In the first column, we have our data values. In the second column, we look at how far each value is from the mean, a bit below, close to, or above the average. In the third column, we square these distances. Squaring serves two purposes. It makes all distances positive, and it makes large deviations count more than small ones. Now we take the average of all these square distances. That average is what we call the variance. It's the mean of the square differences from the mean. There is just one final step. Variance is in squared units, which is not very intuitive. To bring it back to the original scale of the data, we take the square root of the variance. So in summary, variance is the average of the square differences, and standard deviation is the square root of that variance, expressed in the same units as the original data. Let's make this more concrete with a small numerical example. Imagine these are your daily study hours over 5 days: 2, 3, 3, 4, and 8. If you average them, you get a value around 4 hours per day. On the slide, that's the vertical marker on the number line, our mean or typical day. Look at the dots near the average: 2, 3, 3, and 4. Their distances from the mean are small. They're just a little below or right on that central value. These represent typical days, and their square distances stay relatively small. Now focus on the 8. It's much farther to the right, clearly separated from the cluster. Its distance from the mean is large. And when we square that large distance, it becomes a very big contribution to the overall variability. Because standard deviation is built from these square distances, this single faraway value pushes the standard deviation up. In other words, one unusual day with very long study hours makes the typical distance from the mean noticeably larger. On this slide, we are comparing two datasets that share the same average but behave very differently. On the left, you see class A. The scores are tightly clustered around the center. In this case, the standard deviation is small. Most students perform close to the average. That means the results are more consistent and, in a sense, less risky or less unpredictable. On the right, you see class B. The average score is the same, but the dots are spread much more widely. Some scores are much lower, some much higher. Here the standard deviation is large, the performance is more variable, and the outcome is more uncertain. This is the power of standard deviation. It lets us compare the consistency of different datasets that might have the same mean. Exactly the same idea appears in finance, where we use standard deviation to quantify the risk or volatility of investments, and in machine learning, where we analyze the spread of model errors to judge stability and reliability. Now that you have an intuitive idea of what standard deviation is, let's see how often it appears in real work. In data science, standard deviation helps you separate signal from noise. It tells you how much your data naturally fluctuates, so you can judge whether a pattern is meaningful or just randomness. In finance, it's at the core of volatility. The standard deviation of returns tells you how wildly a stock or a portfolio tends to move, which is a direct measure of risk. In machine learning, standard deviation is used to evaluate model errors and to scale features, so that variables with very different spreads don't dominate the learning process. In scientific research, it describes the spread of repeated measurements and the experimental uncertainty around them. Once you understand the standard deviation as a typical distance from the mean, many statistical methods become much easier to grasp. Confidence intervals, z-scores, and hypothesis tests all build directly on this single concept. Let's quickly recap the main ideas before we close. First, standard deviation tells you how much your data typically vary from the mean. Whenever you think how far are my values on average from their center, you're thinking in terms of standard deviation. Second, behind the scenes it comes from the variance. We take the average of the square distances from the mean and then take the square root. That last step is important because it brings us back to the same units as the original data, so the number is easy to interpret. Third, remember the interpretation. A small standard deviation means most values stay close to the mean. A large standard deviation means values are more spread out and the system is less predictable. Finally, this single concept appears everywhere, in data science, finance, machine learning, and scientific research. Whenever we talk about variability, uncertainty, or risk, master standard deviation, and statistics becomes more intuitive. Before we wrap up, if you want to really internalize these ideas and practice statistics with real Python code, I've created a resource specifically for you. Check out my book Statistics with Python 100 Solve Exercises for Data Analysis. Inside you'll find step-by-step exercises on probability, hypothesis testing, correlation, regression, and many other core statistical techniques, all implemented in Python. It's designed to be practical and progressive, making it ideal for students, aspiring and working data analysts, and anyone learning statistics for data science who wants more than just theory. If you found this video helpful, please like it, subscribe to the channel for more content on statistics, data science, and Python, and check the link in the description to learn more about the book. Thanks for watching, I'm Gianluca Malato, see you in the next video.